The purpose of this video is just to give you a just sort of a basic beginning understanding of the idea of a hypothesis test in statistics. This video is intended for a statistics student, somebody who's either in their very first statistics class, maybe their second, possibly their third statistics class if they struggled in their first couple. If you're in your fourth or fifth research methodology or statistics class, whatever is in this video you already know, and it's probably not even relevant, and you're already learning more specific things. So this is really just a very basic procedure for many hypothesis tests that are taught in an introductory statistics class or maybe AP statistics or something like that. So typically your first step in doing any hypothesis test is to make two pretty much mostly mathematical statements, but sometimes they're done in words. We call the first statement the null hypothesis, and we call the second statement the alternative hypothesis. We typically represent the null hypothesis with the capital letter H and this little zero or subscript zero. We'll say H naught or H zero or H sub zero. And then we'll do the alternative hypothesis with a capital H and varying other things as subscripts, capital letter A, lowercase letter a, maybe even a 1 or something like that, okay? And typically what you'll have in the null hypothesis is you'll have a population parameter. It's always a population parameter. We are never, ever putting statistics. We're not putting X bar here. We're always putting some sort of population parameter like mu or rho or sigma or p for a proportion. And then we're almost always putting equals here, and then we're either putting a number over here or some other population parameter. Like we're saying 1 mu is equal to another mu. And then the alternative is typically the same population parameter, and then we either say that it's not equal to, or that it's less than, or that it's greater than typically the same number that you had up here. If you had a number up here, typically we have the same number here, or we'll have another population parameter here if you had another population parameter up here. Moving on to step 2. Oftentimes, in fact almost always, there are some important statistics that are sort of plugins for other formulas, and typically you might have a step where you identify any number of important statistics like the sample size, like the sample mean, the standard deviation of the population, or maybe the sample standard deviation, maybe a sample proportion, maybe a correlation coefficient, or the coefficient of determination. And then you'll typically also identify at some point what's called the level of significance, which we use the Greek letter alpha. And then oftentimes we'll do a rejection rule for how we're going to reject the null hypothesis, which is often what we're aiming to do in research that supports our hypothesis. So we'll basically make a statement that a certain p-value will result in the rejection of the null hypothesis. And it usually goes that if p is less than whatever our alpha number is, then we're going to reject our null hypothesis. Okay. Now a typical step 3 could be that we're going to identify what we often refer to as a critical value, and it's based on some kind of statistical distribution, like the z distribution or the t distribution or the f distribution, or maybe the chi-square distribution. And sometimes what we'll do is we'll take the letter of the distribution, like z, and we'll put a little star or an asterisk on it, and we'll call this the critical value of z, or the critical value of t, or the critical value of f. And this critical value is basically a cutoff score for comparing a test statistic with basically the same letter. So we would compare z to z star, t to t star, and f to f star. And then oftentimes we'll state a decision rule very similar to the one in step 2, where we'll say we're going to reject h sub o or H naught if the test statistic that we're going to see in step 4 is outside of the bounds, oftentimes greater than our critical value of that test statistic. Now, in step 4, we often get the counterpart to the critical value of the test statistic. In step 4, we often calculate the test statistic, like the Z statistic or the T statistic. Now, this number is often specific to the data that we have, whereas the critical value oftentimes comes from maybe a table or from some kind of technology. Now, oftentimes the way that we get this Z or T or F or whatever test statistic we're calculating, it often comes from some formula or we use some kind of technology like a software application or maybe a graphing calculator. In step 4, sometimes if it's necessary, we'll also calculate the standard error, which is often useful for many formulas and also very useful in doing a confidence interval, which is going to come in step 6. Now, step 5 may not always be step 5, but it is going to be in every hypothesis test. And you may do it in one of 2 ways. In step 5, we'll typically identify the p-value that is based on the test statistic that we calculated in step 4. And then what we'll do is we'll typically, after we identify the p-value, we will decide whether we're going to reject the null hypothesis or do not reject the null hypothesis. This reject the null hypothesis or do not reject the null hypothesis is going to be in every single hypothesis test. Now, the means by which you do it can either be by comparing the p-value that you just found to the alpha. So we either compare the p-value to the alpha, or we can compare the test statistic from step 4 to the critical value of the test statistic from step 3. Now, these 2 methods, these 2 both accomplish the exact same task, the same thing. But I want you to know that the p-value method is more common in published research. In most or all quantitative published research, you will see a stated p-value for every almost every relationship, quantitative relationship, almost pretty much every hypothesis that is made. You'll see these p-values all over the place in quantitative published research. And then this last step is not always done, but it is very helpful in learning statistics, is after finishing up with step 5 and making your decision about the null hypothesis, sometimes your professor may want you to confirm the decision that you found with what's called a confidence interval, if you haven't learned about confidence intervals yet. If you have, basically all you do is you create a confidence interval based on the alpha. The alpha helps you determine what the percentage confidence interval is going to be. And then once you have the confidence interval, you basically reject the null hypothesis if some important number, oftentimes that number is 0, if an important number is not on the confidence interval. So if we create a confidence interval and the confidence interval is nothing but positive numbers, well then 0 is not on that interval, and oftentimes that results in you saying reject the null hypothesis. And all you're really doing here in step 6 is you're confirming that you made a good decision or a consistent decision in step 5. If in step 5 you do not reject the null hypothesis, but in step 6 you do reject the null hypothesis, you have done something mathematically wrong. There's an error somewhere. And that's one of the reasons that we can do step 6, is it helps us to confirm that we did all of our math correctly. Well, that's it. That's just a basic introduction to the basics of what the things that you will mostly normally see in any hypothesis test in your statistics class.